Hi everyone, Dr. P here again, and in this lecture we'll take a look at gas stoichiometry. In principle, I'm going to save examples for Friday's in-person class, and then we'll also look at the concept of partial pressures and see what that implies for ideal gases. Alright, so let's revisit the ideal gas law. And of course that was PV equals nRT. P is the pressure, V is the volume, N is the number of moles of gas, R is the gas constant, and T is the temperature. So let's go ahead and take a look at 1 mole of an ideal gas at 0 degrees Celsius and 1 atmosphere. So what I want to do is rearrange this statement here, this equation rather, for solving for volume, because I know the pressure, 1 atmosphere, I know the temperature, 273 Kelvin. Yeah, you have to convert to Kelvin. And I know I have 1 mole of ideal gas. So let's do that. V equals nRT over P, which equals 1.000 moles. I'm just saying we have 4 sig figs here, times R, which is 0.08206 liter atmospheres per mole Kelvin. My moles are going to cancel. My temperature is 273.15 Kelvin. That's the conversion from Celsius to Kelvin. You add 273.15 to your Celsius temperature to get temperature in Kelvin. So my kelvins cancel here, and then that's divided by pressure, which was 1.000 atmospheres. So my atmospheres cancel. And what I end up getting, if I take a look at this, is I get 1 times 0.08206 times 273.15 divided by 1, 22.41. In some places it's listed as 22.42 liters. If I used a slightly different, if I used 273.2, 1 times 0.08206 times 272, I would get 22.42. So your mileage may vary. But this is the molar volume of a gas at 0 degrees Celsius and 1 atmosphere. These conditions are known as STP conditions. That stands for standard temperature and pressure. STP, standard temperature and pressure. Oftentimes in stoichiometry problems involving gases, you'll be told you have 2 liters of oxygen at STP, and you react it with 3 liters of hydrogen at STP. How many liters of water vapor are produced? So something like that. So basically we can carry out stoichiometric calculations for gas reactions if we know pressure, volume, and temperature, because that will enable us to calculate the number of moles. Now we can actually use this to calculate the molar mass of a gas. So N is going to be my number of moles, which is actually going to equal my grams of gas divided by the molar mass. Let's think about it. We have grams divided by grams per mole. So my grams cancel. My moles ends up in the, because I'm dividing by it in the denominator, ends up in the numerator. So I have moles. So this is going to be mass over molar mass. So we'll just call it M over molar mass. So now if I turn my attention to the ideal gas law, PV equals nRT, I can go ahead and substitute in for N mass over molar mass times RT all over V, or mRT over V times molar mass. But M over V equals density in grams per liter. Thus, pressure equals density times the gas constant times temperature over molar mass. Or I can solve for molar mass in this equation, and I'll get density times the gas constant times temperature all over pressure. So if we know D, temperature, and pressure are known, molar mass can be calculated. In fact, for an ideal gas, the density is going to be proportional to the molar mass of the gas. And so that's why if you were to fill a balloon with something that we call heavier than air, basically a gas that is more dense than air, it's just a gas that has a higher molar mass. And I forgot to add up here, are known, to my sentence up there. All right, so we can do stoichiometric calculations. We can do calculations to get molar mass of a gas. Let's see what else we might be able to do. I do want to mention the law of partial pressures, Dalton's law of partial pressures. The same Dalton who came up with Dalton's atomic theory, because the law of partial pressures has important implications for gas stoichiometry. Okay, so Dalton observed the following. For a mixture of gases in a container, the total pressure exerted was equal to the sum of the pressures that each gas would exert if it was alone. So I'll read that again. I've got my definition written down here. For a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. Or, notice I didn't write down that definition, because we can sum it up in an equation. P total, the total pressure, equals P1 plus P2 plus P3 plus, where these pressures are what we call partial pressures. So our total pressure is equal to the pressure if we just had gas 1 all by itself, plus the pressure if we just had gas 2, plus the pressure if we just had gas 3, etc., for all of our gases. Often I would just say the total pressure equals the pressure of oxygen plus the pressure of nitrogen plus the pressure of CO2 plus the pressure of argon, etc. If we're looking at air pressure, for example. So we can use the ideal gas law and do some math. So P1 equals N1RT over V. P2 equals N2RT over V. P3 equals N3RT over V, etc. Okay, now our R, the gas constant, is the same because it's the gas constant. Temperature is the same and volume are the same because everything's in the same container. Remember, this is a mixture in a given container. So, if we look at our total pressure, it equals N1RT over V plus N2RT over V plus N3RT over V plus etc. Or the total pressure equals, I'm going to factor out my RT over V, so I'll be left with N1 plus N2 plus N3 times RT over V, which just equals N total RT over V. So what this is saying is that the total number of moles of gas particles is important, not the identity or composition of the gas particles. And this is going to lead into some insights, important insights for ideal gases, namely that the volume of individual gas particles is negligible, and the forces between the gas particles are also negligible. And we'll take a look at that in the next lecture video. All right, you guys stay safe out there. Bye now.